This conference will now be recorded.
So good morning, Padmini, and welcome back to a fresh new session on market modeling. And and we'll just pick it up from the point where we had started, left it off yesterday. So just in yesterday's discussion, we talked about the time series, the components that a time series has, and we talked about the concept of stationarity. Now, while so we also addressed the question that what are the components which makes a time series non-stationary in nature. So in regards to that, one of the important things that we were looking towards is that uh, so what we were kind of looking towards over there was that what are the things that we would be using, like so what are the things that we would be using for what are the components of the time series models, and how is it that we would be using these components to overcome the problem of stationarity, and also how is it that this problem of stationarity can be solved. So what exactly are the components which leads to making a time series non-stationary? So that is something that we had identified, that we had talked about. However, there are a few basic questions which is left open-ended. That is the first question that we before we decide whether there is a so there is stationarity or not, we need to decide whether at all a particular model would be using time series or not. So can I develop a model using time series? So that's the first question that must come in. So we need to understand that how is it that we should test whether that so whether uh, the time series models are to be developed or not. So do we need to develop a
This conference will now be recorded.
so So one of the important questions that we need to address over here is that how is it that we would identify whether a time series model needs to be developed, right? So that is something which is important over here. So over here, so that's the first question, right? Now, what are the characteristics of a time series model? So basically, uh, let's say I have a time series model, or a time series that I have over here is xt. So the first question that we need to address over here is that will the lagged values of the series being, or whether the lagged values of the series can be used to predict the future values, right? So over here it is xt minus 1 plus delta 2 xt minus 2, like this. If you would have delta k xt minus, right. So this is what we would have over here. We would have xt minus 1, we would have xt minus 2, we would have xt minus k. Now the question is that I can uh, use xt minus 1, xt minus 2 to predict xt if there is some kind of a correlation existing between these terms. So if there is some kind of correlation existing between xt minus 2, and it can be that after a certain lag the correlation does not exist, right? So all we need to understand is that is there a significant correlation So is there a significant autocorrelation between the terms? Right, so is there a significant autocorrelation across the terms? Significant autocorrelation between the lags. So is there a significant autocorrelation between the lags? So this is one of the most important observations that we would need to have, right? So is there a significant autocorrelation? Now the question that comes out is that how do we capture or how do we define the autocorrelation between the term, between the lags, and how is it that we would assess whether it is statistically significant or insignificant, right? So over here, so basically the code autocorrelation between the lags will be, or let's say the correlation between the lags will be defined as xt and xt minus k. Now this is nothing but the covariance between xt and xt minus k by the variance of xt. Right. So this extent of association between the two lags xt and xt minus k, if you see, is nothing but it is something very similar to the formula beta hat that we had seen for the OLS models, right? So therefore, this is nothing but the delta i's that we have written in that equation. So basically, what we need to first understand is that whether there is a significant extent of correlation between the two lags, right? So if that correlation is not statistically significant, right, then we'll not be able to use a time series model. Then what it would mean is that xt and xt minus 1 are independent realizations, right? So if you see, so if we see that, let's say up to last 3 lakhs, last 6 lakhs, last 12 lakhs, last 24 lakhs, uh, if we see that all these lakhs the correlation is statistically insignificant, then what would happen over here is that we would not be able to capture the, so then we would know that xt minus 1, xt minus 2, xt minus k are all independent realizations, and given that they are independent realizations, it is not really possible to model them using a time series model, right? So that is the reason why, so that is the reason why what we would see is that, so that is the reason why we would see that these models are kind of independent of each other. I mean, then we would see the time series model is not really applicable. So therefore, when we start doing, before we start doing this exercise, right? So there is this test which we run in order to understand that whether the lags are, or whether the autocorrelation between the lags are statistically significant or not. Because if that's not the case, then there is no point in developing a ARIMA model, or developing any time series model. So what is basically what is the test that we do then? So the test of what is the null hypothesis of the test? The null hypothesis of the test is delta 1 equals to delta 2 is equal to delta n, versus the alternate hypothesis will be at least one of delta I is not equal to 0. One delta I is not equal to 0. So at least one of the delta i's is not equal to 0. Now from here, one of the next, so one of the important questions is, so over here, so one of the important questions that we would have over here is that of, so over here, so once, so this test that we generally do will be a chi-square test, right? Because it's a correlation test. Right. So a correlation test generally follows a chi-square distribution. So we'll come to that test statistically little later when we are doing it in SAS. Right. So when we try to implement that result in SAS, we can find it. Now the question is that whether the time series is, kind of, whether a time series can be used or not. So one of the very easy ways would be, right. So one of the very easy ways over here would be to do a simple scatter plot, right? So you can take up, now if let's say xt minus 1 has a negative impact on xt, then if you do a scatter plot, right, they should be negatively correlated. So their correlation will show more or less a negative trend. If xt minus 2 and xt minus 1 and xt minus 2 and xt are negatively positively related, then you would expect a positive scatter plot to be there, right? So apart from doing a statistical test, a very simple way of performing the test would be the, so a very simple way of performing this test would be the the scatter plot approach, right? So what we can essentially do is we would use a scatter plot, and based on that scatter plot we will run the exercise, right? So we can do that as well. So over here, what you will have is, so another alternate way of doing this is to use the scatter plot. So the scatter plot will be a graphical way of showing the association between the two lags, right? So if the scatter plot is, so basically what we need to check over here is that whether it has a direction or is it direction and okay. So now if the scatter plot is random and it does not show any direction, then we know that the time series, then we cannot use, although those lags are not significant. So basically what can happen is after getting to 2 3 lags, or like after getting to 6 lags onwards, 7 lag onwards, it becomes random. So we know that up to 6 lags there's a correlation, and the time series that you are developing will be within the last 2 3 lags. So the time series will be, so you can look up to the go back to the last 6 lags, and from there you can start pulling it. So that is one of the things, right? Now, if the plot is random, then we don't proceed forward with it. We know that they are independent realization and you cannot develop a time series. On the other hand, if there is a direction, this will bring us to the next question, that whether the time series is a stationary time series or not, right? And over here we need to understand the tests of stationarity. Tests of stationarity. Now over here, the question that comes out is that how do we test for whether a time series is stationary or not, right? So one of the important things one of the important observations that we have had, and one of the things that we had seen is that the right, that we talked about, the random walk hypothesis, is something or is a model where your which was a typically unstable time series, because if you remember, the mean of the time series was, so if I when we calculated the expected value of yt, right, so the expected value of yt was y0, was y0, and the variance of the series was, so when we calculated the variance of the series, so the variance of the series was t sigma square e. T sigma square e. So this is one of the important characteristics. So one thing that we saw was that the mean was, or the mean was nothing but the initial condition. So when the value, so it started from y0, and from there it started moving up, right? So there was a trend in the variance, and hence the variance of the series was not consistent, was not constant. Hence the one that we saw over here, right, was your non-stationary time series. So what was the original form of the time series which generated this mean and the variance? So the original form of the time series was yt is equal to yt minus 1 plus ut. Right. Zero sigma square e. So this is how the series works, right? This is how the time series looked like. The next thing that we saw over here was that when we calculated the data generation, the data generating process, we came to the following. That yt equals to y0 plus summation ut. Right. So we had yt equal to y0 plus summation ut. So we ran this. So we developed this code, right? So from here, one thing you can see is that this is nothing but y equals to 1 dot yt minus 1, right? So the row over here, this coefficient over here, this delta equals to over here was 1, right? Hence, this process is known as the unit root process. The unit root process. What we have over here is the unit root process. Right. Now, when I talk about the unit root process over here, so one of the important questions again, which comes out, which tends to come out over here is that why is this called the unit root process? So each of these coefficients, right, delta 1, delta 0, delta 2, so these are called the roots of the time series process. So we have this unit root process over here, right? So So over here, one of this unit root process over here is yt equal to y0 plus summation u. So with this unit root process, so whenever a time series is so one thing that we see is that a typical case of a time series of being a non-stationary time series is when the root is 1, right? So when the so if typically, if a time series has a unit root, it is a non-stationary time series, as the variance develops a trend into it. So it is at least a variance non-stationary time series. Now, over here, the question that comes out is that if your time series has a trend, right? So when the time series has a trend in this trend in the variance, right? So then one of the big questions which come out over here is that how do we identify, or how do we so therefore, okay, no, so therefore the problem of non-stationarity ultimately boils down to the fact that whether a particular time series has a unit root or not. So if it has a unit root, then it is a then we would say that yes, this time series is a non-stationary time series. However, if it does not have a unit root, we'll say that no, this time series does not have a unit root process, right? So that is something that we need to understand. So one of the so therefore the question that comes out is that how do we test for this? Okay, so the question is that how do we test whether a time series is non-stationary? So the easiest way to test a time series whether it is non-stationary is to test whether its root, or the whether its coefficient is a unit root or not. So let's say I have a time series of this form yt is equal to rho yt minus 1. plus ut. Right, so let's say yt is equal to rho yt minus 1 plus ut. So I have this. Now the next question that comes out over here is that so how do I test for this? So the null hypothesis over here will be rho equals to 1 so yt equals to rho yt minus 1 plus ut. So after this, so now the test that we do or the test statistic that we use over here is known as the Dickey Fuller test statistic. The Dickey Fuller test statistic, or as we call it, the DF test. Now, the DF test is a pretty simple test, and the test statistic that we follow over here is essentially it's a t-test. So the Dickey Fuller test in itself initially is a t-test. It's a t-test. So how does the t-test look like? So the Dickey Fuller test that we have over here is the DF test that we have over here is as follows. So first you have the rho hat. So the rho hat is the estimated value of rho which you get from your time series model minus the expected value of rho hat divided by the standard error of rho hat. Now the question that comes out over here is that how is rho hat estimated? Now, if I have an autoregressive model that we can see over there, right? So that autoregressive model is the parameters of that will be estimated using uh, the OLS method, right? Therefore, those estimates that we get will be the best linear unbiased estimates, and hence that rho hat is expected value of rho hat will be rho. So your Dickey Fuller test statistic becomes rho hat minus rho divided by the standard error of rho hat. Now under the null hypothesis, the rho will be 1, right? So it becomes rho hat minus 1 by the standard error of row hat. Right. So over here, the Dickey Fuller test is that so the test statistic under H0 will look like row hat minus 1 divided by the standard error of row hat. Right. So now obviously, yes, the normal testing procedures will come to play. So if the p-value is less than alpha, so if the p-value is less than alpha, then H naught is rejected under A. H naught is rejected at the specified level of significance. H naught is rejected at the specified level of significance. So if the H naught is rejected, right, then the time series is assumed to be stationary, and this is a typical two-tailed test that we do. Right. So is this clear, Padmini?
Yeah, all of them.
Okay, so this is one of the most basic tests of stationarity. Now, okay, so Padmini, if it becomes too informative, or if you feel I'm going too fast, stop.
Yeah, sure.
Okay. Okay, fine. So just give me a minute's time and we'll get started. Okay. Sorry. Yeah. So as I was saying, right? So one of the one of the important so one of the most important one of the important limitations that this Dickey Fuller test has, right, is one of the important measures. One of the important limitations of Dickey Fuller test is that this test is applicable only for mostly for AR1 processes. So if you have a single lag, if you have an AR1 process, so once you have obtained the mod for the final model as an AR1 model, then you can use Dickey Fuller to test. However, when you are checking over multiple lags, or you are checking whether time series is stationary for both with both AR and MA components, then the Dickey Fuller test is slightly a limited application, right? So there is an extension of the Dickey Fuller test which is known as the Augmented Dickey Fuller test, right? So there is this one single test which is the Augmented Dickey Fuller test. Right. So the next question that comes out is that how do we interpret the Augmented Dickey Fuller test? So the Augmented Dickey Fuller test is a generalization of the Dickey Fuller test over some k lags. So let us try to check how this Augmented Dickey Fuller test is uh, how this Augmented Dickey Fuller test is different from the Dickey Fuller test. Okay. So let us kind of try to understand this Augmented Dickey Fuller, the basic concept of this Augmented Dickey Fuller test, why this Augmented Dickey Fuller test is important, and what are the factors that Augmented Dickey Fuller test takes in to create the statistic. Now, what Augmented Dickey Fuller test checks is the following. So over here, one of the things that you can see is that uh, for the augmented Dickey Fuller test, we are not actually checking whether white is stationary. What we are trying to check is that the factors which are, so let's say there is a yt and there is a yt minus 1, right? So the change that is happening between yt and yt minus 1, and then between yt minus 1 and yt minus 2, then between yt minus 2 and yt minus 3, so those changes are remaining more or less unchanged. So there is no major changes happening between the two labs. So that is what we are trying to test over here. So the idea that augmented Dickey Fuller test is using is an extension from this particular point, right? Yt and yt minus 1. So basically, let's say there is yt. So over here we saw that this time series, this random walk was non-stationary, right? However, if I try to calculate the first difference over here, if you check the difference between yt and yt minus 1 is ut. Now, this yt in yt minus 1 is nothing but your delta yt. Now, this delta, now when you have multiple lags, it is easier to always check whether this change in yt is constant or not, right? So, what we have over here is that ut follows normal distribution 0 to sigma square. Now, one thing you can see is that this delta yt is stationary because both the mean and the variance become stationary. So it can always be the case that your yt is not stationary, but your delta yt is stationary. So your time series automatically becomes stationary if all the delta yt is at between any two intervals. So yt minus yt minus 1, yt minus 1, yt minus 2, yt minus 2, yt minus 3, they all have constant changes, right? So if the rate of change remains constant, then your time series becomes constant. So that is what the augmented Dickey Fuller tries to check. So one of the component it tries to check is that A0 is the intercept plus gamma yt minus 1. The second check that it does is, so this is where, so up to this point, this statistic is as same as what the Dickey Fuller test had done. But after this, it brings in a new component into it. So it says that so it takes up all the summation of all the lags from 2 till the last lag. So it takes into account the summation of all the changes between any two consecutive lags, right? So it says that the respective coefficient which is there, so beta I delta yt minus yt minus I plus 1. So because we are starting after 1 lag, so we are adjusting that 1 lag over here plus the error term et or ut whatever, where et is normally distributed, right? So the question that comes out over here is that how do you assess, right? So how do you assess this entire thing, or what are the checks that you need to have? So obviously, if this So basically, what you need to check is that this gamma that you have over here. So the test that we do over here is that, so the null hypothesis to ensure that the time series is stationary is that the gamma is 0. The gamma is 0 versus gamma is not equal. So this decides whether, or this is how, or if the gamma is 0, right? Then we say that the time. So if the null hypothesis is accepted over there, uh, so if the gamma is taken to be 0, right? So it means that the summation of all the roots is equal to 1, right? So there is a unit root process. So if you accept the null hypothesis, we say that the time series is non-stationary. On the other hand, if the alternate hypothesis is accepted, we say that yes, it's a, so there are no unit root in the time series. So the objective over here is to reject this null hypothesis. To reject the null hypothesis. Now the question that comes out over here is that why do we have to reject? So why am I saying that this gamma has to be 0? So obviously then if the gamma is 0, then it implies that the root is 1, right? So why is it so? That is something that we will take deeper in the next class, right? So augmented Dickey Fuller test takes into account. So how is it that augmented Dickey Fuller test is differing from this unit from the simple Dickey Fuller test? It is differing from the Dickey Fuller test in the case that uh, that uh, that in the Dickey Fuller test we are just looking into the yt minus 1 lag, but over here you are not only looking into yt minus 1, but also you are looking into the cumulative impact of the historical lags, right? So the historical changes between two lags. So let's say if I is 2, then it is minus 2 plus 1, that is yt minus 1. Then when I is 3, it is yt minus 2. So the changes between all the all any two consecutive lags in the history is taken into account, and if any one of them has a issue, if there is an issue with any one of those lags, then it will then gamma the null hypothesis will be accepted. So that is how the augmented Dickey Fuller test is created. So we'll delve deeper into this test. We'll see why is it that I'm saying that gamma equal to gamma has to be 0 in the next class. So in the next class, we will be focusing totally on the concepts of Dickey Fuller test. We'll talk about the concepts of we'll dive deeper into the concept of Dickey Fuller test, its advantages, disadvantages, and the solutions that we need to provide, right? And we'll use some numerical examples to get a hold of this exercise. So this is what we do in the next class. Thank you. So till then, you can go through these 3 sessions of time series that we have had, and from there we can take it. Thank you.
Sure. Thanks.